Welcome, my dear JEE 2026 and 2027 students. This is your Captain Shreyas on the Vedantu JEE English channel. I hope I'm audible and visible to all of you. And welcome on this lovely Saturday evening where we finally complete the circular motion. And today's lecture is really important because some really different concepts. And usually, I've seen many people do not even bother to see, and suddenly the question comes, and then they realize that, oh, this also is there in circular motion. So, very important things. So, I think this thumbnail is wrong. Sorry, guys. We are going to focus today on, non-uniform circular motion, then the relative angular speed, and the radius of curvature. These are the three things. Okay. Hi, Vijayalakshmi. Good evening. I think your name is Nikilan. How? Okay. Hi, Nikilan. Kritika. Everybody out here, mark your attendance. If you have not yet marked your attendance, quickly in the video, how to mark your attendance, sir? Please tell me how to do it. It's very simple. Just smash that like button down there quickly. Okay. And if you have not yet registered for MV site, please do that because yes, today, tomorrow, last few days going on, lakhs of students giving the examination. The results will be out soon. You will win prizes. You're going to get scholarships. Lot of amazing things happening at the Vedantu learning centers across the country. So make sure you are going and hitting that registration button right now and giving the test today, tomorrow. Okay. Right? Good evening, Dhanush. Good evening, everyone. Yes, that's my quick introduction slide. Okay, so I have been teaching for more than 13 years now. So it's now time to increase my years of experience by one more because you are my 14th, 15th batch already. Okay, so I have a lot of hopes on you. Just couple of months to go for your JEE mains, and I'm really excited. And I know you guys are nervous, but don't worry, I have something amazing planned in the coming few days. Okay, that will remove all your tension. So let's begin with the non-uniform circular motion part first. We have already seen some aspects, so I'll just quickly go through it, okay, so that you remember it. Like, for example, I have told what is uniform circular motion. So when I say that some particle is doing non-uniform circular motion, that means the speed will change. That means the speed will keep changing. If the speed is something here, it will be something else here, and it will be something else only over here. It might again reduce also. Okay, it might stop, it might reverse also. Anything can happen. Okay, so the speed is not constant. The speed is not constant in the case of non-uniform circular motion. And because the speed is not constant, I can quickly say the angular speed is not constant. Angular speed is going to change. It is going to change. And because of that, alpha won't be equal to 0. It will have angular acceleration. Okay? It will definitely have angular acceleration is there. Angular acceleration is going to be present. Now, once there is angular acceleration, you might remember the term tangential acceleration and all of that. So the acceleration along the tangent is called tangential acceleration. The acceleration towards the center is called centripetal acceleration. And this then becomes the total acceleration. So our tangential acceleration, which is nothing but alpha into the radius, even that will not be 0. Even that will not be 0. There will be some kind of tangential acceleration because the speed is not constant. Okay. So tangential acceleration will be present in the scenario. Is this absolutely clear, everyone? Why there is tangential acceleration? Why there is angular acceleration? Because speed is changing or angular speed is changing. All right. So these are some of the uh, terms which you should know or what is happening. Example wise, so many examples are there of non-uniform circular motion. When you turn on a fan or basically a motor stopping, when a motor is stopping, When a motor is stopping, there is change in angular speed, or when the fan is turning on, angular speed is again changing, or the wheel changing speed, wheel is changing speed. So many such examples are there. Okay, so many such examples are there where speed is not constant, it will change, it will either increase or it will stop. Or a giant wheel is there, it is started to move, and then after some time again it stops. So when it's stopping or starting, you can see omega is definitely not constant. Now, just to remind you very quickly, if angular acceleration is constant, if angular acceleration is constant, then you can definitely use kinematic equations. The kinematic equations are valid. That is, final angular speed is initial angular speed plus alpha t. The displacement angular wise is initial velocity into time plus half acceleration into t square, or final velocity square is initial velocity square plus 2 acceleration into angular displacement. All these equations are valid, but in a scenario where your alpha is variable, it is not constant, you do not have constant rate of change of velocity, it is variable. In such scenarios, use derivatives and integration. Use derivatives and integration. Use derivatives and integration. We have already seen that in the last class, just trying to remind you. Okay. Where to get all my notes? Praveen, it's very simple. As you're watching any of my class, let's say I'll go to my previous class, lecture 2 of circular motion. Yeah, let's say for example this one. When the lecture gets over, in a day or two, session PDF link will come in the description box, or you can go to the comment section, it will be pinned over there, one of them. In case it is not there, just message me. This year, that is the practice that we have followed, so that it is very easily accessible to everyone. It might ask you to log in because it is on our Vedantu server. So just enter your free details. It will be downloaded free of course. You don't have to pay anything for it. Okay, clear? All right. So use derivatives or integration, meaning, for example, you have theta, then you have omega, and then you have alpha. If you go from theta to omega, you have to take the derivative. That means d theta by dt. Rate of change of position is omega. From omega, if you have to go to alpha, you take the derivative of omega. Rate of change of angular speed is alpha. The reverse, you have to integrate. So if you go up, then you have to integrate angular speed with respect to time. Okay, so that you will get theta. Just like velocity integration will give you displacement, here accelerations integration will give you that velocity. So this is the logic that you will follow. Okay, everybody with me? Great. So I think with this concepts, we can solve couple of questions coming up on your screen. Here it is. Here it is. If alpha is equal to t square radians per second square, find the change in angular velocity in the first 3 seconds. Find the change in angular velocity in the first 3 seconds. Also find the average angular acceleration. Also find the average angular acceleration. It's a very nice question. Let's try and solve it. Alpha is given as a function of t square. It is very obvious that angular acceleration is not a constant, and because of that, I cannot use any of these equations. I have to go back to derivatives or integration. That is the first thing that you should keep in mind. Okay, I hope this is absolutely clear. Now, if you try and solve the question. Let's see how do we do it. Jayant, so is it, sorry, Arvinda, the full syllabus I think will be completed by November in our Sigma batch, where all of us, along with Pahul sir and PNJ sir, all of us are completing the syllabus. So by November, yes, the syllabus will be done, and then we'll be starting with the revision phase in our Sigma batch. All right. I hope this is clear. Now, how do I find angular velocity from acceleration? If I have to go to velocity from acceleration, it's not derivatives, it is exact reverse process of derivatives. It is integration. So we all know alpha is nothing but d omega by dt. So if you shift the terms, it will look like this. D omega is alpha into dt. Now if I sit and integrate, integration of d omega is integration of alpha into time. So this is what we will be using. We have to obviously be careful about the limits. Here it is asked for the first 3 seconds. Okay. So here I will put the initial angular velocity, and here I'll put final angular velocity, and here alpha is nothing but the square of time. First 3 seconds means starting the time from 0 seconds to 3 seconds. That's how I'll put the limits. Now let's see what exactly do we get after integrating this. Okay, integration of d omega is omega only. So first I will put omega final, then I will put omega initial instead of omega. Like integration of dx is x. So I'll substitute the values in x. Same way, d omega's integration is omega. So I've just substituted them, upper limit and lower limit. T square's integration is nothing but t cube by 3. So instead of time, I'll put the number 3 first, the upper limit. So 3 cube by 3 minus 0 cube divided by 3, upper limit, and then lower limit, obviously subtracted. What is this? This is nothing but your delta omega. That is what is asked. Find the change in the angular velocity. 3 cube by 3 is nothing but 3 square. This is nothing but 0. So 3 square is nothing but 9. So 9 radians per second is your change in angular velocity. Very good, Abhinav. Amazing. Yes, Praveen, crash course will also be launched very soon. We are planning to start somewhere maybe in November or something. Okay, right? Great. Now, the next part. Find average angular acceleration. What is the formula for average angular acceleration? Let's try and recollect. Average angular acceleration. Oh, I remember, it is how much is the change in the velocity upon the time taken. I already know the change, which is nothing but 9, and the time taken is 3. So therefore, the average angular acceleration 9 by 3, that means it is 3 radians per second square. So what a beautiful question. If this was the direct question asked, then you have to find delta omega via integration. Only then you can find the average. Okay, straightforward. Let's go to another question coming up on your screen. Here it is. Say it is given to me that a particle starts from rest on a curved path of radius 4 meters with angular with an angular acceleration of, let's say, 4 radians per second square. Find the tangential, centripetal, and total acceleration after 2 seconds. Find everything after basically 2 seconds. Let's try and think how do we exactly do it. Let's visualize first. Let's imagine a circular path. Okay, there is a particle which is obviously initially at rest at t is equal to 0, but after some time over here, it has some velocity, of course. This is at t is equal to 2 seconds, but at the same time, it also has tangential acceleration like this. It also has centripetal acceleration like this. And what else is given to me? The angular acceleration is given. The angular acceleration is given. How much is it? 4 radians per second square. 4 radians per second square. That is also given to me. So once I visualize it, it becomes easier to solve the question. That's all. Okay. What can we find out? Let's think. I think we can find 80 because radius is also given, and we all know tangential acceleration formula. The tangential acceleration formula is alpha into radius. Alpha is 4, radius is also 4. So tangential acceleration is nothing but 16 meters per second square. Oh, immediately I got 80. So I'm very happy about it. Okay. But for AC, what do we need? V square by R or omega square R? I think finding omega will be better. Okay. And I think we can find out the omega after 2 seconds. But question is, how do we exactly find omega? Well, I can use this particular equation. Omega final is omega initial plus alpha into time. It was clearly given that it starts from rest. So initial velocity is 0, alpha 4, time I think given to be 2. So omega final is nothing but 8 radians per second. 8 radians per second. That is your final angular velocity after 2 seconds. But what will I do with omega? I want centripetal. So coming back to centripetal now. So centripetal acceleration is omega square into r. This is your final omega. So omega final is 8. So 8 square multiplied by r. Radius is also how much? 4. Okay. So what is it? 8 square is nothing but 64. 64 into 4. 64 into 2, 128. 128 into 2, 256. So this will be 256 meters per second square. You got the value of AC also. How many of you got it? Yes, Azad, whatever it is, please let me know in the comment section. I'll definitely help you out. No worries. Thank you so much, Praveen. I'll be waiting to see and meet all of you because even I'll be a part of the crash course. Last thing is the total acceleration, my dear warriors. Now, the total acceleration is the vector sum, but magnitude wise using Pythagoras, it is just AC square plus AT square because total acceleration becomes like the hypotenuse of this right angled triangle. Okay, so AC and AT square you have to do. AC is 256 and AT is nothing but 16. If you want, you can take 16 square outside. I mean, just like this. This is 16 square. Okay, because 16 into 16 is 256. So one more 16 square will be remaining, and here nothing is remaining. All right. I hope everybody understood this step. 256 is 16 into 16. So I've taken 116 outside, but that square was also there. But root of square is the same number. So 16 into root of 16 square plus 1. But 16 square is 256 plus 1 is 257. So 16 root 257 meters per second square is our net acceleration. Okay? That's how we can solve this non-uniform circular motion problem. Fair enough? Let's do next question coming up on your screen. A tangential force of 20 Newton acts on a 5 kg mass which starts from rest on a curved track of 2-meter radius. Find centripetal force after 0.5 seconds. Find the centripetal force after 0.5 seconds. Again, let's visualize the diagram. So we have a circular track. We have some radius. Radius is given to me as 2 meters. It starts from rest, that is at t is equal to 0. There is a tangential force acting. That tangential force is already given to be 20 Newton. The mass of that body is also given. The mass of the body is 5 kg. 5 kg. So because of the tangential force, obviously there will be some kind of tangential acceleration. And after some time, you will notice that that particle definitely will have some kind of a speed at t is equal to 0.5 seconds. And because it has some speed, definitely, oh, by the way, tangential acceleration is still there, no doubt, but it definitely will also have centripetal acceleration. It will now get centripetal acceleration. And once you know centripetal acceleration, you can also figure out how much is the force towards the center. So I have explained myself via the diagram what I should do in the problem. So that is the beauty of drawing, illustrating, drawing charts or mind maps or whatever, a flow chart in the exam in the rough work. Because you get to know what is needed, what is the flow, what else will I need, what kind of laws, concepts, etc. Cool? Okay. So let's see how do we do this. First, I feel we should find the tangential acceleration, and we all know that our tangential force is mass into tangential acceleration. This is as per Newton's law of motion. Force is ma. Force is 20, mass is 5, tangential acceleration I don't know. Therefore, tangential acceleration is 20 by 5, which means it is 4 meters per second square. Once I get tangential acceleration, I think we can find the speed after 0.5 seconds. Multiple ways of doing it. Either you directly use V is U plus AT because alpha is constant or tangential acceleration is constant, or you can, find alpha and then again find omega and then again find V. But I feel that is a lengthier step. We can directly apply kinematic equations. This is a constant. So we are allowed to use kinematic equations, which means final velocity is initial velocity plus acceleration into time, or 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 we can also use final angular velocity is initial angular velocity plus alpha into time. But this is going to be lengthier, guys, because alpha I'll have to find, omega is 0, final angular velocity, from that again I'll find velocity. It is one step extra. So I feel this is a bit lengthy. So I'm not going to do that. Rather, I will use this. Final velocity is initial velocity plus acceleration multiplied by time, which is 0.5 seconds. So this will be 2 meters per second, final velocity. Once I get final velocity, I will find centripetal acceleration. Centripetal acceleration is v square by r. So velocity is, we got 2, radius 2, 2 square by 2 means 2 meters per second square. That is centripetal acceleration. Once I get centripetal, again I can find centripetal force. Centripetal force is mass into centripetal acceleration, again using Newton's laws of motion. F is ma. Mass is basically 5, acceleration is 2. So therefore 5 2s are nothing but 10 Newton. So we have got the answer. We have got the answer. Oh, William, welcome back. Glad you are not late. Yeah, last lecture I remember you came almost towards the end at 7:15 or something. Okay. Cool, guys. Understood? Let's do more good questions. Yeah. All these are non-uniform circular motion. Okay. Let's do this question. This is also very tricky. Okay. Let's see. What is this? A rod of certain length is fixed at the origin. At one end is placed along x-axis at t is equal to 0. It starts rotating about the z-axis in the xy plane in anti-clockwise as seen from the positive x-axis, z-axis. The angular velocity is given by this. Theta is angular displacement. The angular acceleration is. Unnecessarily confusion, but I'll tell you it is very straightforward. This is x-axis, this is y-axis, z-axis is towards you. This is x, this is y, Okay, Z is towards you. If you want, I will just draw it like this. Just because in 2 dimension we can't draw 3D figure. Where is that rod? That rod, one end is at X, along the X axis at T is equal to 0. It starts rotating about the Z axis in XY plane. So this is the rod, and it is over here at T is equal to 0. And from this, it starts to rotate in this XY plane. Okay, that's what is given. And the angular velocity is given by 2 theta square. Theta is the angle which you have displaced. So after some time, obviously, you would have displaced some angle. So maybe after some time, you would have rotated like this. Just imagine like this. So this is the angular displacement that you have done, and the angular velocity is omega, which is given by this particular equation. Question is, find the acceleration. Find the angular acceleration of the rod. Very interesting question. One thing is obvious, that it is not kinematics based because some function is given, so most likely it is derivative and integration based. Okay, right. Let's see, how do we do it? Let's write down the definition of angular acceleration formula wise. I would need alpha. Alpha, as I know, is d omega by dt. Excellent. Do I know omega? Yes, I do. Omega is 2 theta square. 2 is a constant number, so I'll bring it outside. So derivative of theta square. But this is where the problem lies. I can't differentiate theta with respect to time. They are two different variables. So I need to make the variable same. What's the procedure? Mathematical procedure? Yes, it is obviously chain rule. Abhinav, I hope you found whatever you're looking for on YouTube, and I'm so glad you found it here. Telugu gamer, if you're not understanding physics, the first thing you need to do is change your name from Telugu gamer to Telugu JEE. Telugu JEE Capto, or Telugu JEE Physics, or something like that. That is the first step. Stop gaming. Second thing, watch my lectures from the beginning. You will understand. And there's a whole lot of playlists out there. You will understand everything. Watch, my dear. You have time. So I'll change the variable obviously by chain rule. So d theta square by d theta into d theta by dt. D theta cancels anyways. That is exactly the purpose of chain rule. Okay. Now I can differentiate theta square with respect to theta. So therefore, alpha will be nothing but 2 multiplied by derivative of theta square will be 2 theta, and d theta by dt. That is the definition of angular velocity, right? Omega is rate of change of angular position. So this will become 4 theta omega. But that's not there in the options because omega can be resubstituted back. So it will become 4 theta multiplied by omega, which itself is 2 theta square. 4 2s are 8. Theta into theta square will become theta cube. So 8 theta cube, which is option number 4. Option number 4. Got it, my dear students? So this is the level of questions which can be asked in your JEE examination. Chain rule with derivatives and all of that. Right, very good, Kira. Hi, Venkat. Good evening. Let's go to the next amazing question coming up on your screen. There is a body which rotates about our axis and it is having some angular velocity given by this function, and a and b are constants, t is time. The angle by which it rotates before coming to rest. Okay. A lot of things happening. Omega is given to be a minus bt. Okay, that is what is given to me. How much angle will it rotate before it comes to rest? First, let's identify when will it come to rest. So, if it is mentioned in the question, where is it mentioned? Before coming to rest. It is coming to rest. Coming to rest means angular velocity has to become 0. So, a minus bt is obviously 0, right? Therefore, bt is equal to a. Therefore, t is nothing but a by b. So, at this time, the velocity becomes 0. Okay, at this time, at this time, it stops. It it is at rest. It is at rest. Okay, now what do? We have to maybe use this time and substitute it somewhere to find theta. But we have not yet found theta. So I have an idea over here. How about this? Take this equation, write omega as d theta by dt, and that is a minus bt. Take dt on the other side. So d theta will be a multiplied by dt minus b into t into dt. Now integrate this. Now integrate this. Integration of d theta, a is a constant, so put it outside. Integral of dt minus b is a constant, put it outside. Integration of t dt. Okay. And the limits of the integration will be from 0 from 0 to this particular time, which is a by b. Yes, whatever time we found when it comes to rest, a by b, a by b, that is exactly the angle which I have to find when it stops. That is the angle which I have to find when it stops. So it has 0 angle initially, finally it moves by theta angle. And if I substitute the upper limit of time as this value, I will get the angle which it rotates before coming to a halt. Okay, so integration of d theta is theta. So first put theta, then put 0 as the upper and lower limits. A multiplied by dt's integration is time. So put a by b minus 0 minus b. Integration of t is p square by 2. So it will be a square by b square divided by 2 minus 0 square by 2, of course. So therefore theta will be a into a is a square by b minus 0, forget it, minus b multiplied by this is a square by 2b square, b cancels. So we will be getting a square by b minus a square by 2b. Same thing, 1 minus half is half. So therefore theta will be a square by 2 times of b. A square by 2 times of b, that is option number 1. There you go. Option number 1. Okay. So this was a very good question which involved integration and also a concept where it stopped. So we had to substitute that as the limit of that integration. Yeah. No, it is not B option. It is A option. Yes. Very good. Hi, Sai Priya. Very good, Kira. Oh, now you got it. Yes. Hi, Venkat, everyone. Awesome. Cool. Shall we go ahead now to next and more questions coming up on your screen? Let's go with vertical circular motion, the concept of it. See, in vertical circular motion, there can be two cases. One, you have a simple pendulum which is going back and forth, or a complete vertical circle. Examples like, say, Mhm. Imagine this roller coaster where this trolley is going along this path like this. It goes upside down and it comes like this before exiting the loop. So this is a roller coaster loop. This is a vertical circular motion because as it goes up, the energy will change of kinetic because it is gaining potential energy. So speed will change and direction is changing, and all of these things are happening. Or you hold a thread and put a bob and you give it some impulse, you will see it will go around that circle completely. So this is a complete vertical circular motion. So this bob will go like this. Yes, the speed will change. It will lose momentum. It will lose energy kinetic wise. And again, when it starts coming down, again, it starts gaining that energy. That is another kind of motion. Or even this is nothing but a simple pendulum. This is a simple pendulum. This is also vertical circular motion at the end of the day because this ball will go here, it will gain a lot of speed and it will lose speed, stop, and again it will come back like this like this and like this. It will basically oscillate. It will basically go back and forth. That back and forth motion is called oscillation. We'll be studying simple pendulum motion in oscillation chapter separately. Okay, that is a separate chapter in itself. Okay, so today we'll mainly focus on these things, but we'll not worry about oscillation part. We'll just think about the speed or those kind of things, acceleration and all of that. So all these are beautiful examples of vertical circular motion. Now, in all the problems, what happens, I'll tell you, in all these questions of vertical circular motion, no matter where the particle is, maybe now it is here, maybe after some time it is here. Chuma, I'm just drawing some random places here and then here. Maybe here it has some speed v1, maybe here it has some speed v2. Okay, this particular mass is m, and the length of the string or rod or whatever it is L, or radius is R, whatever you want to call. Then the first thing that you can conserve is energy. Mechanical energy is conserved. Mechanical energy is going to be conserved, my dear students. So whatever kinetic energy is there at 1 and the potential energy is there at 1 will be kinetic energy at 2 plus potential energy at 2. Okay, that's number one thing. So kinetic energy will be half m v1 square, right? And this kinetic energy will be half m v2 square, like that. Potential energy you can easily find if whatever places are given. It is here now it has gone here. So the height difference will tell me, or the heights at different places will tell me potential energy. So that is one thing which you will definitely have to use in all these problems. Okay, so energy conservation. Apart from that, free body diagram and all of that might be needed. So free body diagram will definitely be needed to figure out any force, centripetal acceleration, tangential acceleration. So that basic free body diagram is definitely going to be needed. Like for example, over here, a weight might be there, mg might be there, then maybe tension is there, and based on that, you can say, well, there is some kind of tangential acceleration and maybe there is some centripetal acceleration and all of that. Why tangential is there? Because speed is changing, right? It will lose momentum. So that's why tangential acceleration is there along with centripetal. So once you have the FBD, you can easily use Newton's laws and then solve the question. So this is the general way of looking at vertical circular motion. I will give you two specific cases which are very commonly asked. Okay, let's see. Sabri, I am a student from Tamil Nadu and I cleared JEE 2025 by seeing your road series and solving PRKs now in IITJEE. Thank you for everything. Oh my God, I should put this up, yeah. Where are you guys? I think we should put this up. Thank you so much, yaar, Sabri. Means a lot because I'm so glad my YouTube series and of course your hard work is there. And now you're in one of the best NITs, NIT-3G. Enjoy your stay over there. And I'm super duper proud of you. And I'm so glad the Roar series has helped you a lot. And yes, your juniors are here. And maybe next year, many of them will be joining you in NIT-3G. Yeah. So all the best and do well. And so glad you came back. And I think almost every lecture, I'm getting one or two students who come back and tell me, sir, I'm in NIT this, I'm in IIT this, I'm in triple IT this. So I'm feeling very happy. Thank you so much, man. Okay. So let's start with that two specific cases which I was talking about. See, guys, one is where this is a vertical circular motion. This is the pendulum whose length is L. This is that bob of mass M. I have given it some speed, let's say U. After some time, it has to go on the top over here and it has to be able to complete the entire motion. Yes, it should be able to complete the entire motion. Yes, it will lose momentum, but this speed should be enough for it to just barely complete the vertical circular motion. After this, it will again gain speed and again lose speed and again come back, barely completes and again come back. So you might have done this maybe while just as the time pass, you hold something with a thread and you revolve like this and it goes up and down. If you revolve it very slowly, then probably it will go and it will fall off, right? So this is the first scenario. But there are two cases, like I said. The first one is where this particular element is a string. It is a string. And in the second scenario, this is basically a light rod. It is basically a light rod. You might be wondering, what is the difference? Whether it is a string or a light rod? Anyways, masses are not there. How will it matter? Okay, I'll tell you one thing. Imagine if it is a rod and there is a mass on the top and you're holding it from below. Will that rod collapse? Will it bend? No, right? It will, the mass on the top will stay even if I'm holding it like this. This rod will not collapse, it will not become slack. Whereas, imagine this was a string. Can I hold the string from below and expect the bob or mass to be on the top? Zoop, that string will become slack. So, this is the most important point of that problem, where that rod which is there with that mass, the rod will not collapse or become slack. It will not become slack. So, even if it has negligible velocity, negligible speed, negligible speed close to zero, it is enough. It is enough. It is enough to pass the critical top point. It is enough for it to pass that topmost point, because if it passes this, you have passed everything. Okay, got it? So if you pass that topmost point, 100% after that, though, it will gain speed only. Okay, that is the most critical point. So if it passes that, it has completed the vertical circular motion at the end of it. Is that clear, everyone? Yes, perfect. But then what happens for a string? A string, obviously at the topmost point, a string at the topmost point, a string can slack or basically lose tension. That is why for a string, you need some minimum speed such that tension is maintained, such that tension is maintained. Tension is maintained. Without that, it will not be able to complete the circular motion. So it's now obvious that for a string, I will need a larger push at the bottom so that that bare minimum speed is there at the top. Whereas for a rod, I wouldn't need that speed so much, because even if it goes at the topmost point with zero speed, zero means not exactly zero, 0.005 meters per second also, it's okay. It will be able to complete because it will not become slow. This is the main difference. Slack means it has lost tension, like you hold a string, right? It loses tension. Like, say, for example, do I have a string somewhere? Oh, I don't have a string. I'm just searching for a string, guys. I'm so sorry. Don't have a string here for some reason. But yeah, just imagine, man. Like, I take a string and I hold it like this. It is tight, it is taut. But if I don't hold it, it will become loose. It will become slack, like that. Is that okay, Kira? Now, did you understand it? What it means by slack? Okay. So, what do you do in both these scenarios? First of all, if you talk about what is a string, right? So, at the topmost point, let's talk about it. At the topmost point, what is that bare minimum tension needed? So, when you are at the top, the free body diagram will look like this. There is tension over here. There is mg over here, and there is centripetal acceleration, and this is some minimum speed which will be required at the top. So from this, we can see tension plus mg is mass into centripetal acceleration, and therefore tension will be m into AC minus mg. But for the string to not become slack, tension should be obviously more than or equal to 0. Okay, a tension should be more than or equal to 0. Therefore, m into AC minus mg should be more than equal to 0. Therefore, AC will be more than G. M has got cancelled. M and M just got cancelled. Take G on the other side. Is that right? What is centripetal acceleration? It is V square by radius. So therefore, you can see V square will be more than GL. Therefore, at the topmost point, speed should be more than root GL. In ways, we can say minimum speed is root GL. This is at the top. You have to remember this formula. Okay, minimum speed at the top for a string is root GL. But for a rod, it is negligible speed. Keep that in mind. So velocity is negligible at the top. Okay, the minimum speed is negligible for a rod at the top. This is very, very important because the rod cannot become slack. Once we get this, we can use energy equation. Let's use energy equation, guys. So initial kinetic energy plus initial potential energy is final kinetic energy plus final potential energy. Initial kinetic energy is half mu square. Initial potential energy is 0. I will assume this as 0. So final kinetic energy is half m. What was that speed? We just got that speed as root gl. So half m root gl was the speed square plus final potential energy. This is L, this is also L. Total height is 2L. So mg into 2L, mgh. Okay. So therefore, what do we get? Mu square by 2 is mgl by 2 plus 2mgl. This will become 2 plus half is 2.5 or 5 by 2. So 5 by 2 mgl. This is mu square by 2. As you can see, this 2, this m just gets cancelled. Therefore, that minimum speed will be root 5 GL. This is that minimum speed which is needed at the bottom. This is the minimum speed which will be needed at the bottom, guys. Okay, everyone, fine till this point? Yeah, this is the minimum speed which will be needed at the bottommost point. Bottommost point. Perfect. Yes. By the way, the same equations are also valid. Whatever I just wrote for a string is also valid for a circular loop. So even if I have a circular loop, this is a vertical circular loop in which maybe some vehicle, some trolley is going like this. Okay, it will have some speed u here. As it goes here, the speed will reduce. As it goes here, this is the most critical point. It should have some bare minimum speed. See, at the topmost point, you should ensure that the normal is more than 0 for it to not lose contact. For it to not lose contact. This free body diagram is very much similar to this free body diagram where instead of normal you have tension and tension should be more than 0. So whatever analysis we have done for a string pendulum vertical, same analysis is valid here. So therefore the minimum speed at the top, therefore the minimum speed of the top for this loop will be still root GL, and minimum speed at the bottom for it to not lose contact anywhere and complete the circle will be root 5 GL. So these formulas, whatever we got, root 5 GL and root GL, are also valid for a circular loop. Is this clear? Everyone give me a thumbs up and smash the like button in case you have forgotten to do so. Okay? Great. Having said this, what is it the formula for a rod, you again apply same kinetic energy, potential energy equation. Energy is conserved. Final energy over here. Initial energy is half mu square. Potential wise 0. Kinetic wise at the top it is negligible. Plus potential energy is mg 2l, height plus height, L plus L, 2 height or 2L. Okay, so half mu square is 2mgl. As you can see over here, mass just cancelled. Therefore, u square is 2 into 2gl. Therefore, u will be root 4gl. This is the minimum speed at the bottom. Without this speed for a rod, you cannot complete the vertical circle. As you can see, root 4gl is definitely less than root 5gl. It is expected because for a loop or for a string, I will need more speed to make sure that the minimum speed is maintained at the top. But for a rod, I don't have to maintain any such speed at the top. So that is why that speed is slightly lesser than root 5gl. Then, okay, understood? Pakka? Clearo? Great, great. Let's see a question on this. Imagine you are designing a roller coaster or a Hot Wheels track, and the track is like this, a beautiful track like this. And you have taken a small cart or a vehicle over here and of mass m, and you have gently pushed it, gently pushed it. This particular track is perfectly smooth, so no friction at all. And it is also told to me that the radius of this particular loop is r. If you take the lowest point of that loop and this point from where you have gently pushed, this is basically h, and this is what has been asked. So what should be the height so that when this trolley comes below, it enters the loop and completes the circle without losing contact? So this height you have to find without losing contact anywhere. It should complete the track. Okay, let's try this out. Let's try this out. How many of you have played with Hot Wheels or sat on a roller coaster like this? It starts going down and zoom, it goes up and down like this. Yeah. So if you are a racetrack designer, or sorry, roller coaster designer, then you need to do this analysis. So let's see, how do we do it? First of all, if I push it gently, that means negligible speed, by the time it comes down, it will have some good momentum and good speed. And here, for it to complete the circular track, obviously at this point it should have root GL speed, and at this point it should have root 5 GL speed. So how much potential energy should it have, or how much height should it have so that it gains this sufficient speed? It means I have to use energy equation. So initial kinetic and potential energy is final kinetic energy and final potential energy. Initially gently pushed to 0. Potential energy is mgh. Kinetic energy at the bottom is half m root 5gl square. Potential energy at the bottom is nothing. Okay. So as you can see over here, this mass and this mass just got cancelled. We get gh is equal to 5gl divided by 2. Gg also gets cancelled, and wait a minute, it is not L actually, it is basically R, because it was a radius, right? This is R and this is also R. Okay, yeah. So Gg gets cancelled, so it will become 5R by 2. That is the answer. So if you keep this height as 5R by 2, basically 2.5R, then it will be enough for it to complete the circular motion. Yeah. So this is also a good type of question that you can get. Great. Now, another kind of question which I want to give you as homework, same type. Okay, this was asked in JEE 2025. Something similar to what I just explained to you over here, that in all these questions, either you have to draw FBD or use energy equation. Same thing. And based on the concept of the string theory, minimum speed at the bottom is root 5 GL, at the top it is root GL. They have asked this particular question in JEE 2025, where some body of mass and some radius is given, and it has some speed at the bottom, which is 10 meters per second. What is the ratio of the energy at B and C? So you know the kinetic energy here. When it reaches here, it will lose some energy, kinetic. After it goes here, it loses even more energy, kinetic wise. So if you use energy equation, you will get the answer. So just do that. I'm 100% sure you will get the answer within few steps. Okay. Okay. All right, Praveen, I'll have a look at it. I'll have a look at it. Okay. Okay. Great. So let's do the next concept, which is nothing but the radius of curvature. Let's do the next concept, which is the radius of curvature. Yeah. So what is this radius of curvature and how do we exactly find it? See, if you have any curved path, any curved path, it's made of small arcs. It's made up of one arc here, then one arc here, and then maybe one arc here, and then maybe one arc over here. Any curved path is nothing but a sum of small arcs, one after the other, and each of this arc is part of an imaginary circle. Like for example, this might be a part of this circle, this arc might be part of maybe this circle over here, maybe this arc is part of this circle over here, maybe this arc is part of this circle over here. So each of this arc is a part of an imaginary circle. And hence I can say any curved motion is nothing but multiple small circular motions. So I can say that the motion in 2D along any curved path is 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 the is nothing but many small circular motions, but every circle is different. It's going from one circular motion to next circular motion to next circular motion, like that. Everybody agrees with this? Everybody agrees with this? Okay. Now this circle or these circles will have their centers. These circles will have their centers. That center is called the center of the curvature. That means the center of that circle is called the center of curvature. And if you draw the radius at all these points, if you draw the radius of all these circles at all these points, they are basically called the radius of curvature. They are basically called the radius of curvature. As simple as that. That is called radius of curvature. Very easy? Yeah, very good. Awesome. So now the question arises, how do I exactly find the radius of curvature? Many times I might be needed to find that out. So the logic for that is simple. Say you have been given some curved path and you want to find the radius of curvature at some random point. Let's say over here at this particular point. At that particular point, you should definitely know one thing, and that is the velocity. You should definitely know what is the velocity at that point to find out what is the radius of curvature. to find out what is the radius of curvature. How will velocity help me find the radius of curvature, you might ask? See, velocity and radius are related by V's omega r, but omega is not known, or or centripetal acceleration. Yes, centripetal acceleration is nothing but v square divided by the radius. I know the speed. To find radius, I just need to know AC. So say for example, I happen to know that the total acceleration at this location maybe is this much, or maybe this much, or maybe like this, or maybe like this. Chumba, I'm putting some random thing. This is nothing but the net acceleration of that particular body. Jet acceleration will have two components, one along the tangent and one perpendicular to the tangent, that means along the radius. This particular component will be the centripetal acceleration. So if I know the total acceleration, I can find the centripetal acceleration. From that, I can find the radius. So if I know A, the component, the component, the component of the total acceleration along the radius, or towards the center, that component will give me AC, and velocity will be already known to me. That's how we can find out whatever the radius of curvature is. Is this process clear? I'll demonstrate this to you via an example, but the process should be clear. Okay. So whatever acceleration is there towards the center will be the centripetal. From that, we can find the radius of curvature. The technique is very, very simple and straightforward. Yeah. So mv square by r is the force, not radius. Centripetal acceleration is v square by r. Mass never comes, Dilip. Okay. Mass comes means it will become force. Okay. I'll give you an example. Look at it. Imagine this is your ground from which you have thrown a ball like this with some speed u, making angle theta, and this ball is going to go in a curved path like this. Okay. The question is find the radius of curvature just after projecting and find the radius of curvature at the highest point. Find the radius of the curvature at t is equal to 0 and highest point Okay, that is the question. Let's see how do we exactly find this out. Let's first imagine things. Okay, this is my imaginary circle over here. At this point, I want to find it. Do I know the speed already? Yes, I know the speed. Then for the second scenario also, let me again draw that imaginary circle. That imaginary circle will be here somewhere like this. Yeah. Let me think about the radius, how it will look like. Maybe something like this over here and maybe something like this over here. Okay. Are you able to visualize this, guys? This is the radius in this case and this is the radius in this particular scenario. So I know speed. Oh, in the second case, I don't know. The first case only I know. And I want to find the radius. In the second case, I think we know the speed at the topmost point. What is the speed at the topmost point of a projectile? If it is u at the topmost point, only horizontal component will remain, which is u cos theta, which is only horizontal component which will be remaining. So now the only thing remaining is to figure out what is the acceleration. From that, we can find the component and then my job is done. Okay, let's see. I know any particle motion under gravity will have acceleration due to gravity. So acceleration due to gravity will be like this, obviously. So this is basically your g, which is nothing but the total acceleration. Not just here, even for this guy, the total acceleration will be downwards, Yeah, and that will be basically g. That g will be acceleration, total acceleration. Okay. What should I do next? Split the acceleration into components, but only worry about that component which is towards the center. I can see there are two components. One component is like this along the tangent, but I'm not interested in that. I'm interested in that component which is towards the center. This is what is of my interest. This is obviously tangential. I am interested in centripetal. Okay. Think if this is theta, obviously this angle will be 90 minus theta. Naturally, again, this particular angle will be theta again. So, if this is g, this is closer to theta, centripetal acceleration will be g cos theta. Centripetal acceleration will be g cos theta. We just heard about centripetal acceleration being v square by r. Centripetal acceleration is g cos theta, which is v square by r. Therefore, r will be v square by g cos theta. That's the answer. How easy it is via this method. No complex derivatives, functions, etc. needed. Directly you get the answer. V square by g cos theta. Got it? Yes. Awesome. What about the topmost point? Not difficult at all. In fact, the acceleration is already towards the center. So this itself is centripetal. So we don't have to split it. So AC is V square by R. AC is itself G. Velocity is U cos theta. And this is R. Therefore, R will be U square cos square theta divided by G. So we got that answer also. So any kind of question like this, always find out velocity, find out acceleration, split up the acceleration into components, worry about only that acceleration which is towards the center. Cool? Wow. Yeah. Yeah. Is it real that you have done classes when you have affected by COVID? Yes, I think so, Dilip. I think I suffered COVID 2 times. One during the Delta wave, one during the Omicron. Delta, I think during March or April or something, and then Omicron, I think during Jan, February time. Yes, I mean, I've been teaching on YouTube since COVID, right? October 2020 or November 2020, that's when we started the channel, and it's now 5 years. It's 5 years since I'm here on this channel for all of you and continuously taking up classes. I don't think that, oh, I have taught this last year, oh, I have done this, oh, just watch that, watch this. I still do it because I know you guys love me, you guys want to see me live and all of that. Okay. So thank you so much, guys, for showing that love and affection. So that was the radius of curvature. Last thing is a relative angular speed. This is pretty decent concept, can be used in multiple places. See, I'll give you 3 scenarios. This is the distance r, and in each case, there is a particle which is moving in 3 different directions. V, V, and V. It's right now making some kind of angle, let's say theta. If I ask you, in these 3 scenarios, where do you think the angular position will change? What will our answer be at that moment? Okay. I know in this first scenario, it's obvious that this particle will move here. So obviously angular position will change. So definitely there will be some kind of angular velocity. And if you imagine this to be a part of a circular motion, if you imagine this to be a part of some kind of circular motion, V becomes tangential, R is the radius. So omega will be nothing but V divided by R. Very simple. That is the angular velocity of that object with respect to this particular point. Here, in this scenario, omega will not be there because angular position is not changing. So in this scenario, omega will be 0 because from this point at the next instant, you will be just here. Theta is not changing. Theta is constant. So theta is basically constant. So derivative will be 0 or omega will be 0. In this scenario, what you should do is, it's obvious that you'll have to split the velocity into two components now. Don't worry about that component. Don't worry about that component which is in perpendicular direction or along the radius. Only worry about that component which is perpendicular to the radius. Okay. So then we will understand that, okay, there is definitely some angular velocity, and that will be velocity in this direction, which is v cos theta, and the whole thing divided by r, because I know that at the next instant when the particle reaches here, that angular position has changed not because of this component, but because of the v cos theta component. I hope this is absolutely clear. R is not infinite, R is a fixed value. But the thing is, even though R changes, angle is not changing, and omega is V by R or d theta by dt. So there is no d theta by dt here. That is why omega is 0, not because R is infinite. R is a finite value. Problem is V cos theta or V component in this direction is not there. Great. Sir, but what if, imagine you don't have something like this. Imagine you have 2 points separated by some distance. Let's say I call it as r, and this point has some velocity here, and this point has some velocity, let's say here. Okay, let's say this is some velocity v1, let's say this is some velocity v2, let's say this is theta 2, and let's say this is example theta 1. Can we now find relative angular velocity? Can we now find relative angular velocity? I think so. In the previous scenarios, one of them was at rest, the other point was moving. Here, both the points are moving. So if I have to find the relative angular velocity, all I need to do is split up the velocities into two components. See, one of the components will be like this, perpendicular, and that is what will change the angle, like this one and this one. The other component is pretty useless. This component is of no use to me, because of that component there will be no change in theta, there will be no change in the angle. Just imagine if this velocity is there, this particle will keep going like this. Angle wise there is no change. This velocity, it will just keep going like this, angle wise no change. But this green, as soon as they are there, angular velocity is existent. So how much is this? This will be v1 sine theta 1, and this will be v2 sine theta 2. So let's say, for example, I make this point as my point of reference. So for that particular point of reference, okay, for that particular point of reference, as you can see, at some distance of r, this particle will have some velocity which is already perpendicular. And how much will that be? Forget the red ones. Just think of two particles going in opposite direction. What will that relative speed be? That relative speed will be nothing but v1 sine theta 1 plus v2 sine theta 2. That's it. Just addition of both the speeds, isn't it? So hence, what will the angular speed be? The angular speed will be equal to v by r, right? Because v is omega. So it will be v1 sine theta 1 plus v2 sine theta 2, whole thing divided by r. That's all. That is the answer. If the speeds were in the same direction, then you will subtract. That's obvious. But the concept, I hope you understood how to find a relative angular velocity. Okay. Radius of curvature of a straight line is infinity. Yes. Yes. Very true. Kira. Okay. Sir, completion means to complete only theory or problems. Ranganathan, when I say completion, it means theory, watching lectures or having those notes, plus doing the basic questions and basic PYQs of mains level. Some, not all. Even if you do 5, 10, 20, 30 PYQs, okay, but just do something. That at least you should be doing. Okay. Okay, great. Perfect. So that's the concept. So I have a brilliant question in front of you. Tell me what is the relationship between, if there are two particles, 1 and 2, 1 and 2, okay, separated by some distance. If I say angular velocity of 1 with respect to 2 and angular velocity of 2 with respect to 1, which is the correct symbol between them? Okay, first is equal to, okay, second is equal to, okay, I'll do one thing, rewrite it. What is the right symbol between them? Is equal to, is with a negative sign, is never equal to, okay, which of them is the correct option? One of them is right. So think about it and tell me, guys. Omega 1 2 is relative angular velocity of 1 with 2. Omega 2 1 is angular velocity of 2 with respect to 1. So what do you think is correct? Yeah, tell me, guys. Equal but in opposite direction. Okay, is that so? Let's understand. Imagine I make myself sit over here. So for this point at this distance, maybe that particle will appear to go like this. Chumma, I'm putting some random direction. This is the relative velocity of 2 with respect to 1. So how will omega be? Omega will be like this. This is angular velocity of 2 with respect to 1. Is that okay? Now just imagine I make myself sit over here. So if I sit over here and then look at the other particle, which is like this, then that particle's velocity will be in this direction, exactly opposite. This will be velocity of 1 with respect to 2. Magnitude wise, it will be the same. But what will be omega? Omega will be like this. This will be angular velocity of 1 with respect to 2. Tell me what will be the magnitude here and here. Omega 21 magnitude wise will be V21 by whatever this length or distance is. So divided by L. And same thing over here, omega 21 will be V12 divided by L. Magnitude wise, isn't both of them the same thing? Aren't both of them the same thing? Because V21, because what did I say? Velocity of 2 with respect to 1 and velocity of 1 with respect to 2, magnitude wise is obviously the same thing. Is obviously the same thing. So magnitude wise, omega 12 and omega 21 are the same. But what about direction? Omega 21 is clockwise. Omega 12 is also clockwise. That's the common mistake which many kids make, and many people write B as the answer, which is wrong. Actually, it is A. Omega 12 is equal to omega 21. There is no negative in between. Yeah, both are clockwise. That is the crux of the problem. Many kids do not know this. And that is why I am teaching you all of this, so that you do not make any mistakes in the actual examination. Cool? So that was the concept of relative angular velocity, my dear warriors. Relative angular velocity. So we have done relative angular velocity, radius of curvature, non-uniform circular motion, vertical circular motion. This chapter is done. See you next time for rotational motion and some big surprises for Diwali on YouTube for you from all the three teachers. Stay tuned on the channel. Okay, big dhamaka is coming, which will probably, change your mind if you have given up. Okay, so make sure you're liking and comment below, and the PDF will be